Hello everyone, welcome back. In this video, we'll be discussing about the last problem of today's biweekly contest, Power of Heroes. The problem states that you are given a array nums representing the strength of some heroes. The power of a group of heroes is defined as this mathematical expression, where I0, I1 up to Ik are the indices of the heroes in the current group. So basically, the power is defined as you will take the max strength in the group, square it, and multiply it with the min strength of hero in the group. Now, as you can imagine here, like there are multiple groups possible, right? So you need to return the sum of power of all non-empty group. And since the sum can be very huge, you will have to return it modulo 10 to the power 9 plus 7. So let's take an example. Let's say this is the three heroes and the strength of first hero is 2, strength of second hero is 1, and strength of third hero is 4. Now how many groups of heroes are possible here? Total 7 non-empty group of heroes are possible here. These are the 7 non-empty group: 2 1 4, 2 1 2 4 1 4, and 2 1 4. Now you will find the power of each of these groups. So what is the power of this group? Min of maximum, like max of strength square multiplied by min of strength. So here there is only one hero, so min and max both are equals to 2. So the power would be 2 square into 2, which is 8. Similarly here the power would be 1 square into 1, which is 1, and 4 square into 4, which is 64. Now this is bit interesting. Here we have two heroes, so power would be max of both these squared. So max of 2 and 1 is 2. So 2 squared multiplied by min, which is 1. So multiplied by 1. So the power of this group of heroes is 4. Right. Similarly, you will find the power of other groups as well, and you have to return the sum of all the powers, and the sum would be 141, and hence here 141 is the answer, right? So hope the problem statement is clear. Now how to solve this? So firstly, this is what we have been asked, right? We have to sum this mathematical expression for every possible group of heroes, right? Now how many group of heroes possible? Each of these heroes can either be present or may not be present in the group, right? So in total, there are 2 to the power k minus 1 groups possible. Why minus 1? Because we need to only consider non-empty groups. So there will be one group which is empty. Basically, we choose not to take everything in that group. So these many number of groups are there. So in total, the groups is order 2 to the power k, where k is the number of heroes, or let's say it is n, where n is the number of heroes, right? Now, for each of these group, you will find out the power. Now, how to find the power? You will have to find out the minimum and maximum. Both you can find out in order and time, right? So, for each of these group, you will require order and time to find out the power, and this would be your final time complexity. Now, this will surely not pass because n is up to 10 to the power 5. So, 2 raise n would not pass at all, right? We need to optimize this. Now how to do this? So as we can see here, the order of element doesn't matter because we need to choose some elements and then we have to find the power. So order of element doesn't matter. Now, as I always say, if order of element doesn't matter, the very first thing you should do is you should sort the array, because solving the problem on a sorted array sometimes or a lot of times is more easier than solving the problem in an unsorted array. So let's just sort the array, and this is the new array which we will work with, right? Now we can't we can't enumerate all the groups. So what is the next possible thing? Next possible thing is, let's try to enumerate what is the output. So we can't enumerate what is the input to these expression, right? So let's try to enumerate what could be the output of this expression. Now output of this maximum would be one of these nums of I, right? Similarly, output of this minimum would be one of these nums of I, right? So let's try that. Let's say this is the minimum and this is the maximum, right? Now notice that, like, we can clearly say that what would be the minimum, what will be the maximum, because we have sorted the array. So it is always true that minimum index would be before the maximum index, and hence we can say if this is the minimum, maximum we can choose anything on the right, right? So let's say you fix what is the minimum and what is the maximum. So you know what is the output of this expression? Output of this expression would be 3, right? And similarly, you know what is the output of this expression? Output of this expression would be 1, because that's what you have fixed, right? Now, how many such expression? So first of all, what is the power? Power would be 9 into 1, which is 9, right? So power would be 9. Now, how many such groups are there which have power 9? That's what you need to find, right? So here, look at, we have chosen this as minimum and we have chosen this as maximum, right? Now everything in between may or may not present in the array. These two must be present because we know this will be the minimum and this will be the maximum. So these two elements must be present in whatever group we form. Now the middle ones may or may not be present, right? So that's where what we can say is there can be four groups possible which have these constraints satisfied. So basically minimum is 1 and maximum is 3, right? So here you can see there are four groups. In one we have taken this one, in second one we have taken this 2, in third one we have taken this 1 and 2 both, and this group doesn't take any of the 1 and 2. So we have total 4 groups possible. And again, why 4 groups? Because there are 2 elements and each of these elements may or may not present in the array. Now because these 2 elements are already there in the given set, we know that the given group, whatever group we will form, that will not be empty. So that non-empty criteria is already satisfied because these two elements is something which is always there. So number of groups that is possible here is 2 to the power 2, right? So this is what we have with power of 9. So what we can say, if this is the minimum and this is the maximum, the total number of groups that will have this same power would be 2 to the power 2. So we can simply add 9 into 2 to the power 2 to the answer, and we can do this exact same exercise for every possible minimum and maximum. So what we can say, currently I and j, I is minimum and j is maximum. We can try all possible values of I and j and do this exact same thing. Basically, we'll try to find how many groups are there which have the same power with I as minimum and j as maximum. And how to find groups? We have simply seen that number of elements in the which is there in the middle. We can simply take 2 to the power of that, and that will give us how many groups are possible, right? So what is the pseudo code for this? Pseudo code would be very simple. It would look something like this. We will iterate over every possible minimum and we will iterate over every possible maximum. So if minimum is starting from 0, maximum would start from minimum plus 1, right? And now for, we know how many such groups will be there which will have this as minimum and this as maximum. How many groups will be there? 2 to the power of mx minus mn minus 1, right? Basically we just find out how many numbers are there in the middle, right? Now notice that this is true only because we have sorted the array. If we haven't sorted the array, we have to like do something else here. Because we have sorted the array, we know everything in the middle are actually smaller than this and greater than I. So that's where this is true. Now we once we find out the number of arrays, we can simply add the power that many number of times to our result, right? Now what is the time complexity of this entire thing? Time complexity would be order n square, uh, assuming that you can simply pre-compute this 2 to the power of x for every possible x, because number of possible x here is only n, right? So you can pre-compute that, and hence the complexity here would be order n square. So you brought the complexity down from n into 2 to the power n to order n square. But n square also would not pass slightly, and you have to do something better. Now, if you haven't come up with n square solution itself during the contest, I would strongly encourage you to try coding this n square solution as well. That will give you much more clarity. Now, if you have watched till this point and you are following this channel regularly, I would strongly encourage you to pause the video and try to reduce the complexity from n square to order n by yourself. This is very simple refactoring of this inner loop. We have done this many times in this channel. So I would encourage you to pause the video and try to remove this inner loop by yourself, right? So hope you have thought about it. The removal is very straightforward here. So simply we need to refactor or take the commons out. So here you can see what is common. This array mn is common. Basically what we are doing here is we are adding to result some value, like some j, let's say j, this is j, right? So this is j, mx equals to j. So let's say we are adding j square into 2 to the power of j minus I minus 1, right? And also we are multiplying this I. Now we are doing this for different j's, right? That's what we are doing in this entire inner loop, right? Now currently it is j, then it will be j plus 1, then j plus 2, and so on and so forth, right? Now what is common here in this entire expression? 2 to the power minus I and I is common across all these sums, right? So we can simply refactor this. Take this as a factor, 2 to the power minus I into I, right? And write something like j square into j plus 1 into 2 to the power j minus 1, right? And similarly j plus 1 square and 2 to the power j and so on and so forth, right? So that's what we can do, right? So that is exactly what we have to do. So that is exactly what we have done here. We have simply refactored this inner loop, right? Now this inner loop is just calculating this summation, right? And after this summation is calculated, we can what we did was simply multiply this array mn into 2 to the power minus mn into the sum and then add it to the result, right? Now, why we have done this? Because we don't want any of the mn factor in here. If we are able to remove all the mn factor from here, we can simply apply prefix sum and pre-compute this entire for loop beforehand and use the prefix sum to actually find the value of this entire for loop in just order one time, right? So because this entire for loop is now independent of mn, it only comprises of mx, we can simply take this out and compute the value for every possible mx. And what we need here, we need the summation across mx in the range mn plus 1 to n. So we can simply, like, the value of this would be prefix of n minus prefix of mn, right? So we can simply use prefix sum and compute this value directly, and hence this entire for loop would be replaced with an order 1 operation, and the entire algorithm would now reduce from order n square to order n, right? So just to reiterate what we are doing, let's just take this as an example. We we were trying we were previously having two for loops, and in the inner for loop we have both the expression mn and mx, and in arrays as well there is both mx and mn. Now we want to remove this inner for loop. To remove inner for loop, what we are saying is, somehow, if we know what I is, we have to somehow find the sum across all j's in order one time. That's what we want to find, right? So that's where what we have done, we have simply removed the mn factor from this for loop so that we can pre-compute this before this for loop is started completely, and we can simply move this to order one. Now, I would strongly encourage you to pause the video and try to code this entire thing by yourself again. Uh, There is one catch though. Let's just quickly discuss that as well. So we have to multiply 2 to the power minus mn, right? And because each of these multiplications we would be doing modulus m, so doing division is actually not straightforward, right? Basically you can't like, let's say you have to take modulus of 3, right? Now you are taking 2 to the power 4 and you have to divide by 2, so the result would be 2 to the power 3, you know. But if you have taken modulus 3 already, so 2 to the power 4 would be 16 modulus 3, which would be 1. So you have to take 1 by 2, which is something you haven't, like you can't actually simply do a division operation to find this value. So what to do? So the problem statement is we have to find out x divided by 2 to the power i modulus m, uh, where x is like x is divisible to the power I, to the power I, but because x is already in modulus with m, the current value of x may or may not be divisible by 2 to the power of I, right? So that's where Fermat's little theorem will come in. So only thing you need to remember is the theorem states that a to the power p minus 1 is congruent to 1 mod p. Basically it says that you can simply replace 1 with a to the power p minus 1, where p is the modulus and a can be any number as long as a is not divisible by p, or in other words a is co-prime to p. So if a and p are co-prime, you can simply replace 1 with a to the power p minus 1 and that is allowed, right? So here let's say this is a, right, and this is p because this is modulus p. Now here m is a complete prime because m is 10 to the power 9 plus 7, so 10 to the power 9 plus 7 is actually a prime number. So a prime number and a number a will always be co-prime, right? Because unless this is exactly equals to m, the GCD of m, GCD of 2 to the power I and m will never be equals to m, right? So that's where we are sure that 2 to the power I and m are actually co-prime. So we can simply apply Fermat's little theorem here. And what we can do, we can say that, okay, we will multiply 1. And because 1 is congruent to a to the power p minus 1, we can simply say 1 is actually replaceable by y to the power m minus 1, right? Now we can remove like this y and do this m minus 2. That's what we have done in the next step. So now this is something we can simply do multiplications and figure out the value, right? So this is how you will do divisions in case of modulus, right? So hope this point is clear. Like this point is basics if you know about the number theory already, but in case you don't know, this is the proof of that. So anytime you need to do division by some number, you can simply do y to the power m minus 2 as long as y and m are co-prime. In this case m is prime and y cannot be equals to m in any scenario because y is equal to 2 to the power I, right? So that's where we say that y and m are always co-prime, and we can simply replace this division by a multiplication of y to the power m minus 2, right? Now next we'll look at the code. Again, if you haven't tried it out yet, I would encourage you to pause the video and try to code this entire solution by yourself. So this is the code. Now these are two functions, divide by y. As we have already discussed, this divide by y will only work when y and modulus are co-prime, and it will return you the value of x by y modulus mod, right? And what we are doing here, we are simply doing x multiplied by y to the power mod minus 2. Basically first power will do x power y modulus mod, so it will give you the value of y to the power mod minus 2, and we can simply multiply with x and we'll get x divided by y modulus mod, right? Now this fast power is actually finding out this power in log n time. Now how to do this, it's something we can discuss later, but basically it's just a number theory thing. You can write y in binary, and whichever bit is set, you can simply add that number to the results. For just to give you an example, let's say you have to find out 3 to the power 10, right? So you will write 10 in binary format. So what is the value of 10 in binary? 1010, right? Now what you will do, you will simply say that the value of 3 to the power 10 will be equals to the value of 3 to the power 8 plus sorry, multiplied by 3 to the power 2, right? Basically uh, you just take this uh, numbers that are set in the binary representation. Now like what you can simply do, you can simply come from the backwards. So this is 3 to the power 0, right? You know 3 to the power 0 is what is the value to the power 0. You can sorry, this is 3 to the power 1, right? Now you can simply find out 3 to the power 2, 3 to the power 4, and 3 to the power 8, and so on and so forth. So this all you can simply find in just one operation. And how many operation you have to do in this order? Log n, because number of bits here would be log n. So this entire, like there are total log n bits, and you are calculating this 3 to the power x log n number of times and multiplying log n numbers here. So the entire thing would work in log n time. So this is like just the quick explanation of fast power. That's what we are doing. We are simply finding out that 3 to the power of x, and if that bit is set in y, we are multiplying it with the result, right? Now, once we know how fast power and divide by y is working, we can look the solution. The solution is straightforward. We just sort the array as we have discussed. Now we find out the prefix sum for this inner loop. Now, what this inner loop is, again, array mx square multiplied by 2 to the power mx minus 1. So that's what we have done here. Uh, 2 to the power of mx minus 1 is there. So we have simply started with 1 for 2. So minus 1 is already taken care of here. And here what we are doing, we are just doing prefix of j minus 1 plus 2 to the power of mx minus 1 multiplied by nums of j minus 1, nums of j minus 1, basically mx square. Now, once this entire thing is done, we can simply iterate over mn. So mn is this particular value. Sorry. And inside this, we can simply find out the sum of this entire for loop, right? And what is the sum? Sum would be prefix of n minus prefix of j mod plus mod modulus mod, like this plus because we are doing a subtraction operation, and this entire thing can be negative as well. So that's why we have done plus. After that, as you know, we have to divide by 2 to the power of mn. So that's what we are doing. We divide by y to where power 2 actually is the value of 2 to the power of mn. And once this entire thing is done, we have to multiply this with mn as well, and we sum up this with result. Now this entire thing will take care of the sets or the groups which contains at least two numbers, right? But a group can contain one number as well. We have seen that. So for all the one numbers, the value would be that number itself. So mx and mn both would be that number. So basically the value would be that number cube. So for all such group of a single member, we will do this. So I forgot to explain this while explaining the solution, but I think you get the idea. So that's it. If you have any doubts in this particular problem, feel free to post them in the comment section below. I will try to answer. If you like the video, give it a thumbs up and do subscribe if you haven't already. And I will see you in the next one. Thank you.